Alrighty, folks, so welcome to the first lesson of the first unit of Math 30-1. So our first unit here is going to be about functions, something you've seen before, but now, going a little deeper with them and actually looking at how we can perform operations with functions and then later on transformations to those functions. So at the beginning of every lesson, you'll kind of find, a list of the big ideas, the questions you should be able to answer at the end of the lesson. And this kind of acts as like a little checklist you can basically use, right? So after the lesson, after you've done your practice, it's always a good idea to come back to this and just kind of check in with yourself, right? Can you add and subtract functions? If not, that's okay, but that lets you know, all right, that's something I need to work on because I'm supposed to be able to be able to do that after this lesson, right? So these are always a good thing to come back and check in with yourself. Did I get the big ideas for today? All right, well, let's jump in. All right, so like I said, we're going to be talking a lot about functions. I mean, really throughout the course, but in the first unit here, we're really taking functions and looking at the different things we can do with them, right? How can we, perform operations with functions is our main goal today. So in order to do that, let's start out with a quick little reminder, a little review of what is a function anyway, because having a good understanding of that will help us then be able to, well, perform operations with them. So what's a function? It's really like, it's an expression or a rule that defines a relationship. That's really what a function is. It's a relationship between two variables. It's telling us about how one variable depends on another. So it's the relationship between a dependent variable, that's the one that, depends on the other. Typically we call that y. Of course it could have other letters or other names, but we often call that the y. We say y depends on x, or we say y is a function of x. And again, that just means y, the value of y is going to depend on what the value of x is. So the independent variable, the one that doesn't depend on the other, is usually x. So we put in x's, and then what y comes out of the function depends on the x that we put in. So a function only ever has one y value output for any individual x value that we input. I think of a function, it basically acts like instructions, right? It's defining a relationship between y and x. And it's like instructions. It says if you put in an x, follow these instructions and you can figure out what the corresponding y value is for that x. So it's to find out what y will be when you plug in an x. So let's just take a look at an example here. Here's one you know and love from Math 20. We studied this a lot in Math 20. This is the function y equals x squared, or as we would say in function notation, f of x is equal to x squared. Now, at its core level, what this is saying is here is how the value of y depends on the value of x. Okay, so let's just break this down a bit. This f of x, now be careful, it's not saying f times x, right? It's saying f of x. It's a function of x. Okay, so this really is just telling you the name of the function. You could see different letters here. F is the most common, but it could be g of x, h of x, k of x, whatever. All it's saying, we sometimes have more than one function going on, so we want to give them a name so we understand which function we're talking about. Okay, so this is f of x. And what we're saying here inside these brackets, notice what I said there, f of x. This is a function of x, meaning that it depends on x. We are going to input x's. So we're going to put x's into the function, okay? And then this equation part, it tells us what the function does to those x's, right? In order to get an output. So all this function does, we put in an x and it squares it. It raises it to the power of 2. Right? So breaking it down, that's all we've got here. This is a function called f. What do we put into the functions? What's our input? Oh, it's x values. And then what do we do to those x's? These are the instructions. It says square it, and whatever you get, that's your corresponding y value. So just looking at, what that looks like when we actually do it, if we evaluate this function for some different x inputs, right? Again, f of any x is just going to be x squared. The output will just be whatever happens when we square x. So we could write it like, let's say I wanted to put in 1 for x, right? And figure out what the output of the function would be. That's just saying f of 1. Well, we know that we're going to take our x value and square it, right? So f of 1, we're putting in a 1 for x, and 1 squared is just 1. So this is saying when x is 1, the value of the function, the y output, is 1, because 1 squared is 1, right? If I put in a 2 for x, f of 2 is going to be 2 squared. I'm going to put in a 2 for x, and 2 squared is 4. So f of 2 is 4. When x is 2, y is 4. Notice how, the value of y depends on x is. If I were to ask you what's y, you would say, well, it could be lots of things. It depends on what you put in for x, right? If we put in 1, y is 1. If we put in x being 2, y is 4. Input 2, output 4. Right? When x is -1, well, -1 squared is also 1. So we can put in an x of -1 and we get out a y of +1 because -1 squared is +1. And so you sometimes hear this idea of a function as almost like a machine. That's an analogy that's often used, especially when you're first introduced to functions, right? We stick x's in and it always spits out specific y's, right? It almost converts these x inputs into the corresponding y output. But that at the end of the day is all a function is, right? We input a independent variable and the function outputs a responding or a dependent variable, okay? So again, just a reminder here, the value of the function, when we say that, we're saying what its output is, right? We write that as f of x, and it's talking about the y value, what came out of the function, right? The output that results when a specific x is input. And for a function, since each x input results in a specific f of x output, right? Each x gives us a specific y. We can actually just pair them up to make ordered pairs, right? Input, output, which each then correspond to a point on a graph, x, comma, y, input, comma, output. And all a graph of a function is, sometimes we forget this, right? That the graph of a function is actually just showing us every combination of points. It's just a collection or a display of every ordered pair of the function. Every single point where the x value and the y value work with that function's equation, right? So the points on the graph are really just showing us inputs on the x-axis and then the corresponding outputs on the y-axis. So that's what this example down here is doing. It's doing it for the function we were just looking at. F of x equals x squared. Y is equal to x squared. What the graph of y equals x squared is showing us is every single point where the y value is just equal to the x value squared, right? So here's like a table of values using this function, the one we were just talking about, f of x is x squared. Well, when x is -3, the function f of x, or y, is going to be 9, because inputting -3, well, -3 squared is -3 times -3, that's +9, right? -2 squared is going to give us +4. -1 squared, +1, 0, 0, 1, 1, 2 squared is 4, 3 squared is 9, right? It gives us these sets of points. And all we mean when we say the graph of a function, right, is to look at every place where the x and the y value kind of work with that function's equation, right? Everywhere in this case where y is equal to x squared. So you can see that's all we're doing. We're mapping it out. We could see that all of these points would lie on the graph of the function f of x equals x squared, because at all of these points, the y value equals the x squared. We will not, for example, find the point, 2, 5 on the graph. You can see, right? 2, 5 is not going to be on this graph. Why? Because 5 does not equal 2 squared, right? 4 equals 2 squared, so that point is on the graph, right? If we graph y equals x squared, we should not see it pass through 2, 5. And that's what the graph of a function shows us. So we could, we probably know this shape, the parabola that we get if we graph y equals x squared. Again, that's just showing us every single place where the y value equals the x value squared, right? Like we can see 2, 7 is not on the graph because 7 does not equal 2 squared. But 3, 9 is on the graph because 9 does equal 3 squared. And there's all these places in between that aren't like nice numbers, but they are still places where the y value equals the x value squared, right? As we mentioned earlier, okay, F is the most commonly used letter, but keep in mind, and we'll see lots of different letters used, any letter can be used. It's just a name, right? It's like Fred. You could be called Fred, you could be called Arnold, you could be called anything, right? It's just the name for the function so that we can keep it straight. So you've seen functions a lot, right? In Math 10, you studied them quite a bit. You looked at linear functions. In Math 20, we spent a lot more time with quadratic functions, though we also did look at linear functions in Math 20 as well, okay? And they have those names because when we draw their graphs, they make straight lines or they make parabolas when we graph them. So for example, right, all this graph here is showing us is everywhere where the y value is equal to 3 times the x value plus 2. Don't believe me? I mean, let's take a look here. Look, let's look at this point. How about right here? X is 1, y is 5, right? And it is on our graph. Well, 3 times 1 is 3, plus 2 is 5. So sure enough, here the y value is equal to 3 times the x value plus 2. And that's why that point is on the graph of y equals 3x plus 2, right? Again, 110 is not on our graph because 10 is not equal to 3 times 1 plus 2. Okay, so every single point along that graph is just a point where the y value is equal to 3x plus 2. And this is, again, why we think of functions almost like instructions, right? You could put in any x and it would tell you what y corresponds with that via this relationship. This is how y depends on x. 3 times the x plus 2, right? In this one, it's a different relationship. Different relationship needs a different equation, right? Now, how does y depend on x? Well, you have to square the x and subtract 8, and that gives you the y. See what I mean? Different relationship. Different equation, different relationship. It depends on x in a different way than this one did. So for this one, what do? We square the x input, and then we subtract 8. That gives us the corresponding y values. This is the function h of x. So again, put in 0. When x is 0, I'm going to square 0. That's 0. And 0 minus 8 is negative 8. Sure enough, the point 0, negative 8 is on our graph, right? I mean, you could do this for any point you like here. Even look, 4, 8. It looks like 4, 8 is on our graph. Sure enough, 4 squared is 16. 16 minus 8 is 8. Right? So 4, 8 makes a lot of sense to be on our graph. If the relationship between y and x needs to be x squared minus 8. 16 minus 8 is 8. Okay. Again, same idea here, right? Just kind of repeating ourselves at this point. Different relationship between y and x. The graph of k of x is going to show us everywhere where when we input an x value and the y value comes out to being that x value squared times negative 3, and then subtract 4 times that same x value, right? That is what this graph is showing us. That's what we mean when we say the graph of a function, and a function is just a relationship between a dependent variable, our y, our function value, right, and an independent variable, our inputs, our x. So there's a little quick recap of what a function actually means. Let's try an example here where we want to actually determine the value of a function at specific values that we're inputting. So we would say we want to determine the value of these functions at a specific input, right? Basically, what is y going to be for these x's? So they gave us two functions, and they defined them by the equations f of x equals 2x minus 1, and g of x equals x plus 2. So again, the rules here, the instructions are take your x, multiply it by 2, and subtract 1, and that tells you the corresponding y for this relationship. That's how y depends on x. Same thing here, except we're just going to add 2 to our x. So it wants us to figure out f of 2 and g of 2. Well, f of x is 2x minus 1. So for f of 2, I'm literally just going to put in 2 for my x. So wherever I see an x, I'm going to put in a 2. So 2 times 2 minus 1. And therefore, f of 2 is equal to, well, 2 times 2 is 4. 4 minus 1 is 3. So f of 2 the value of the function f at 2 is 3. When x is 2, y will be 3 for that function. Input 2, output 3. All right, let's try it for g of 2. Well, g of x is just x plus 2. So what's g of 2? Right, well again, this is just saying, the function says, I can tell you what y is, you just got to put in an x and I will show you how to get the corresponding y, right? This is the general form of the function. Put an x in, add 2, and I'll give you the corresponding y. So now what we're doing is we're saying, all right, let's put in 2 and see what the y is when x is 2. Well, 2 plus 2, and therefore g of 2 is just going to be 2 plus 2 is 4. So there we go. We worked out the value of f of 2 and g of 2. So that wraps up our little, review of what a function is, the basics of a function, right? We input x's and the function tells us how to get the corresponding output, the corresponding y value, okay? Let's now start moving into some Math30 stuff here and actually do operations with the functions, okay? So we've seen how to input stuff into a function, but we can actually do stuff with multiple functions where we add functions or subtract functions. That's what we're going to start out with here. We can add, subtract, multiply, and divide the functions themselves. We're going to start with adding and subtracting, like I said. We can do this graphically. We'll see some examples like that today. Or we can just do it even for specific outputs, okay, by doing the operations to the y values. Remember, we're adding the function. We're adding f of x to g of x, for example. That's referring to the outputs, right? The result of that function. So we are adding the y values. When we say the value of the function, don't forget, that means we're saying the result, what we got. When we input an x, the value of the function, right? That's just referring to the result, the output, the y value. So we're always going to be doing the operations to the y values, the outputs. We can also do it with the equations to get kind of more a general form. So it depends on what we're looking for. If we're just trying to find what happens when I add these functions for a specific value of x, right? Like maybe you can look ahead, we're going to do here. Well, then I can just take whatever f of 2 is and add g of 2. But we can also do it to the two equations themselves and just give ourselves a general new equation for the sum or the difference of those two functions. And that will work at any x. Essentially, we're building a new equation based on what happens when we add the equations for f of x or subtract the equations for f of x and g of x. Let's just jump in here and take a look at what it actually looks like, okay? We can represent this in a couple of ways. So nothing here other than just the format of how it looks. You'll see it both ways, so just be comfortable with both ways, okay? Sometimes we write it as f of x plus g of x. To me, that's a little more intuitive. It's saying what we're actually doing, right? We're taking f of x, we're adding whatever g of x is. Sometimes, though, we write it like this, f plus g of x, still just saying it's a function of x, and that function of x is the result of adding two other functions of x, f plus g. So don't miss the fact here that this is still a function of x, right? F of x was a function of x, g of x was a function of x. What we now have is a new function of x that results from adding these other two functions of x. So this is still a function of x, it's just a new one we've created by adding two others. Similarly, for subtracting two functions, we could write it as f of x minus g of x, or we could just write it as f minus g of x. Those mean the exact same thing. These do not mean anything different from each other, okay? It's still referring to the same idea. We can just represent it both ways, and you will see it both ways, so don't get thrown off by that. All right, so for this example here, we're gonna see it both ways, okay? We'll look at it both ways. So using f of x equals 2x minus 1 and g of x equals x plus 2 from the previous example, it wants us to determine f of 2 plus g of 2 in two different ways. So the first way, we're just going to perform the operation on the outputs. The second way, by performing the operation on the equations, okay? So we already worked out the outputs. Remember, we figured out that f of 2 was just 3 and g of 2 was just 4, right? We worked out that f of 2 was 3 and g of 2 was 4. So to perform the operation on the outputs, we really are just going to add these two, right? That just means f plus g of 2 is going to be 3 plus 4, right? Which is, of course, 7. So f plus g of 2 is 7. Because f of 2 is 3 and g of 2 is 4. When we input 2 to f, we got an output of 3. When we input 2 to g, we got an output of 4. So adding f of 2 to g of 2, we just get 3 plus 4, or 7, right? Again, we also could have represented it this way. This is the same thing as saying f of 2 plus g of 2, right? Same idea, same result. It's 3 plus 4. We know f of 2 is 3. We know g of 2 is 4. So f of 2 plus g of 2 is just 3 plus 4. But we also can do this in a more general way by performing the operation on the equations themselves. Now, you might say, okay, why would I do what we're about to do here? It seems just like a little more work, and you're right. It honestly kind of is when we want to just find a result like this. It is honestly a little bit more work, but sometimes we don't want to do it at a specific input. We just want to find a new equation for our combined function, right? So I'll show you what I mean here. Let's try it out. We know that f of x is 2x minus 1. Right? We don't have a specific input there. We're just saying that's how the y depends on x, right? It's 2 times the x minus 1. And same goes for g of x. If I don't input a specific value of x, I could just say, well, it's x plus 2. Okay, g of x is just whatever we put in for x plus 2. All right, so what would f plus g of x be then? Well, f plus g of x would just equal f of x is 2x minus 1. So I'm just going to put that in. 2x minus 1. And g of x is x plus 2. I like to use brackets here just to make sure I don't miss any, negatives or anything when I'm simplifying, right? So now we're just actually adding their equations to give ourselves a new equation, the equation of the combined function, the result of adding these two. So that means that f plus g of x is going to be, I've got 2x minus 1 plus x plus 2, just kind of adding those terms there. And then I could combine like terms to simplify this a bit. So this means f plus g of x is 2x plus another x gives me 3x. And then negative 1 plus 2 gives me a positive 1. So f plus g of x is 3x plus 1, right? Now, this is a pretty powerful tool. Because yes, in this specific case, we want to know what f of 2 plus g of 2 is. So to be honest, this would probably make the most sense for what we would do, right? Work out f of 2, work out g of 2, and then add them, okay? But what if we just wanted to figure out a general way to find the result of adding f of x and g of x at any value of x, right? That's what we've just achieved here. Because we've just now figured out, well, if I add these two functions, the result is just 3x plus 1, right? And so now, yes, we are going to be able to figure out what f plus g of 2 is. But we could also figure out what f plus g of 7 or 10 or negative 126 would be, because we've worked out the general equation for adding the function f of x to g of x. It's just 3x plus 1. So now, just to show you that we still get the same thing, right? Let's work out what f plus g of 2 is. So 3x, so 3 times 2 plus 1. Oh my goodness, look at this. F plus g of 2 is 3 times 2 plus 1. Well, that 3 times 2 is 6, plus 1 is 7. So notice we get the same result, right? Same result. So again, right, if we're just looking for f of 2 plus g of 2, this is probably a little bit quicker, right? But keep in mind, now we've got a general equation for what f plus g of any x could be. And it will work out the same. We still got the same result there. All right, let's try subtracting them. So still using the same two functions, determine f minus g of 2, right? Well, again, we know f of 2 is 3. We know g of 2 is 4. So what's f of 2 minus g of 2, right? Well, f of 2 minus g of 2 is just going to equal f of 2 is 3, g of 2 is 4, so 3 minus 4, which gives us negative 1. Right? It's pretty straightforward. That's really what we're doing, right? Take f of 2, subtract g of 2. And then we can do the same thing, but more generally with just f of x or g of x, right? For any x value by performing the operation on the equations. So what is f minus g of x? Just like before, we added the two equations, except now you can probably put together that we're going to subtract them. So now I'll do 2x minus 1, subtract x plus 2. And what's that going to give me? Well, I'm going to have 2x minus 1, and then be careful. Remember, we're subtracting this whole stuff in the brackets, right? So I'm subtracting this term, and I'm subtracting that term, right? If you like, you can think of it as we're distributing the negative 1. But that means I'm subtracting x, and then I'm subtracting that positive 2. So f minus g of x is 2x. Let's combine like terms here. 2x minus x, that just leaves me with 1x, or x. And then negative 1 subtract 2, combine those like terms. Negative 1 subtract 2 is negative 3. So in general, the equation for f minus g of x is just x minus 3. Now that's great. That could work for any x. That would allow me to figure out at any x what's the result of subtracting this function from this function, or sorry, other way around, this function from that function, okay? But we were asked to find f minus g of 2. So f minus g of 2 is just going to be, like always, right? That means input 2 for x. So 2 minus 3. And f minus g of 2 is therefore, look at this, same result, negative 1. 2 minus 3 is negative 1, right? Good news. That's good. It should be the same, right? It should be the same because all we're doing here, subtracting the outputs of the functions at that specific x. Here, first we're subtracting the general functions first and then inputting our specific x, right? Same result, basically just reversing that order of steps. Evaluate the function, then subtract, or subtract and then evaluate the new function. Just flipping our step 1, step 2 between these two. And that's really all there is to adding or subtracting these functions, right? Obviously, we can see more complex equations or trickier examples, but don't overcomplicate this for yourself. We really are just either adding the inputs or subtracting the inputs, sorry, the outputs, adding the outputs or subtracting the outputs, or adding the equations or subtracting the equations themselves, right? And then sometimes inputting that x to figure out what the result is. So let's take a look at this one. This is actually from a real diploma that was written by Math 30 students. I believe this is from 2019. Okay, so this is kind of the example, the type of thing you might see. You'll find them peppered throughout the notes. We'll look at examples from the diploma. Okay, but we've got graphs now. The graphs of two functions, f of x and g of x. So always read carefully. This is f of x. This is g of x. Okay. Now a new function, h of x, is defined by h of x equals g of x minus f of x. So remember, when we do this, like when we take two functions and subtract them, really what we're doing is we're just making a new function, right? This had some rules, this had some rules, and now the new rule is that we take those two and subtract them. So h of x is just some new function. Now we don't have an equation for g of x, we don't have an equation for f of x, but we've actually got something even better. We've got the graphs of f of x and g of x. Whenever they give you the graphs, it's actually really nice. At first it throws students off, but think about what a graph shows us. Remember, all the graph shows us is every output at each x input. For example, on f, we can see that when, x was negative 3, y was positive 1. Right? Well, that's great because if I want to end up subtracting f of x from g of x, I can see what f's value is at every individual x input. And I can also see, because I have the graph, what g's value was at every individual x input. Right? I mean, not to get too far ahead of myself, but I can already see to do g of x minus f of x, well, when x is negative 3, I'm going to do 0, because that's g's value. G of negative 3 is 0. Subtract positive 1, because that's f of negative 3, right? So h of negative 3 will just be g of negative 3 minus f of negative 3. It'll be 0 minus 1, right? So that's our plan here. We've got all the outputs. We've just got to subtract them in order to sketch the graph of h of x on the coordinate plane below. Okay, probably a good strategy here would be to just make a little table of values. So I'm just going to say for some different x's, what is the value of f of x? I'll just do f of x in red to keep it straight. F of x. What is the value of g of x? Do that in blue. And then, what is the value of h of x? And h of x is just f of x minus, nope, sorry, g of x minus f of x. That would have been bad. G of x minus f of x. We would get a different result there, right? Subtraction, the order matters. F of x minus g of x would have given us different numbers than g of x minus f of x. So there's a, something to look out for. Okay, so I'm just going to do, for the x's I'm going to choose, let's just look at what we can see. For f, it looks like we can see from negative 4 up to, well, forever. So let me start at negative 4. Let's say negative 4, negative 3, negative 2, negative 1, 0. Okay, and notice g of x stops. Like when x is 0, it just stops. Notice there's not an arrow there continuing it. We're going to circle back to this idea when we talk about the domain of these combined functions, okay? What x's are we allowed to input? What y's are we allowed to get out, okay? But you can already kind of see, for example, if I were to do x being 1, positive 1, well, notice g of x doesn't exist when x is 1, right? It doesn't. We would actually say it's undefined. There's no definition of what g of x is when x is 1. It stops when x is 0. So just to show you what I mean, and again, we're going to circle back to this in some more depth later, but worth bringing up now. If I were to say, what is h of x when x is 1? Let's look. Well, f of x when x, oh, we actually can't even see it, so that's maybe a bad example. Whatever, f of x would be some number, right? Some number. But g of x is undefined. So if we tried to think about what h of x would be, it would be undefined minus some number. Now, it doesn't matter that we are subtracting some number. This is still, it's undefined, right? You can't say that like undefined minus something is defined. How could that be possible, right? You can't get a defined answer if it was undefined to begin with, right? It's still undefined. It depends on something undefined, and therefore it itself would be undefined. So just bringing that up, we'll kind of put that on the back burner for now, okay? But a little preview of what we're going to have to think about when we go to graph this thing. Because again, g is not defined beyond x being 0. If x were 1, g of x doesn't exist. And therefore, since h of x depends on g of x, h of x also doesn't exist when x is greater than 0, right? Same goes on the flip side over here for when it's negative 4, right? When f is negative 5, for example, or when x is negative 5, for example, f of x doesn't exist. It stops right there. So h of x is not going to exist when x is less than negative 4 either, right? Because h of x requires us to have a defined f of x. We can't do g of x minus undefined and get a defined answer. In between those two, in between x being negative 4 and x being 0, it looks like we're safe though, right? It looks like they're defined there. So let's just go ahead, get back into it here. When x is negative 4, f of x is negative 2, right? That's the output, so negative 2. And g of x is, looks like positive 5. Right? When x is negative 4, g is positive 5. So I'm just going to go through and do that for all of these values of x. When x is negative 3, f of x is positive 1. When x is negative 3 here, g of x is 0. Continuing on, when x is negative 2, f of x is positive 2. When x is negative 2, g of x is negative 3. When x is negative 1, f is positive 1. G is negative 4. X is negative 1, g is negative 4. And finally, 0. When x is 0, f of x is negative 2. And g of x is negative 3. Okay? And again, we can't keep going. When x is 1, right, g of x is undefined. So h of x is also undefined. Okay, so all we're doing here now is to figure out h of x, right? Again, do you have to make the full table? I mean, you could possibly just kind of look between the two y values. For a written response like this on a diploma, though, you want to show your work, show your thinking, so I think the table's a good idea. Plus, it just helps us make sure we're not making a mistake. So g of x minus f of x, right? That's what we're doing for h of x here. So when x is negative 4, we're going to do 5, g of x, minus negative 2, f of x. So we would literally do 5 minus negative 2, which is just 5 plus 2, right? Minus negative 2 is plus 2. So 5 plus 2 is 7. And there we go. We've got our first point. That is a point on the graph of h of x, right? The graph of g of x minus f of x. When x is negative 4, y is 7. H of negative 4 is 7. So I'm just going to add that point to my graph. When x is negative 4, y is 7. And we're on our way to graphing h of x. So I'm going to repeat that same exact process for some more points so we can add points to our graph and start to get an idea of the shape. And then we'll be on our way. So same thing, g minus f, right? So I might not show as much work here. G is 0, f is 1 when x is negative 3. So h of negative 3 is going to be 0 minus 1, or negative 1. Just doing g minus f, because that's what h of x is. They told us that. All right. Negative 3 minus 2. Negative 3 minus 2 is negative 5. Let me add those points to my graph. X is negative 3. H of x is negative 1. So negative 3, negative 1. There's my next point. And when x is negative 2, y is negative 5. So when x is negative 2, the value of h of x is negative 5, right there. All right, getting back to it here, let's do two more. G minus f, so negative 4 minus 1, also negative 5. So when x is negative 1, y is negative 5. And last one here, when g of x is negative 3, f of x is negative 2. When x is 0, so negative 3 minus 2. Oh, sorry, negative 3 minus negative 2. Negative 3 minus negative 2. So that's negative 3 plus 2, so that's negative 1. So when x is 0, y is negative 1. All right, now, key thing here, something that a lot of students lost marks for on the diploma, right? If you go look at this released diploma, you can see where students lost marks. And I'll just first do it correctly, right? Based on what we can see, that seems to be roughly the shape of it, right? I think that would get full marks. That's a reasonable shape for our graph based on what we can see. Here's where a lot of students lost marks. They did this. They added a little arrow. But remember, that doesn't make sense here for what we said here, right? G of x stops being defined at x equals 0. So we can't continue h of x past 0, right? It's based on something undefined when x is greater than 0. And same thing for when x is less than negative 4, right? When x is less than negative 4, f of x is undefined. So h of x can't be defined either. How can h of x be defined if it depends on f of x and f of x is undefined there? Okay, so this is actually what we should do. We should stop here and have these clear endpoints. We don't want to extend that graph. It literally, h of x just doesn't exist there. It's not defined beyond x being -4 and x being 0. All right, so that is the graph of h of x. We've drawn y equals h of x, we could say, right? That's showing us everywhere where the x value gives us, you know, this result, right? Everywhere where the y value is just the result of taking the output of g of x and subtracting the output of f of x. Now, they did also ask us to identify the coordinates of the y-intercept. Well, I mean, the y-intercept, again, that's where it crosses the y-axis, right? It is where x is 0, the value of y when x is 0. So we can see, I mean, even from our table of values, the new intercept is at 0, -1, and our graph backs us up there, right? So our new y-intercept, or I'm calling it new because it's the result of combining g and f, but it's the y-intercept of h of x. Maybe that's a better way to word it, right? So the y-intercept of h of x is at, now it said coordinates, so make sure you give coordinates, right? 0, -1. There we go. All right, so moving on to another example here. Two functions are defined by f of x equals x squared minus 3x minus 4, and g of x equals 2x minus 1. They want us to determine a simplified expression for h of x equals f of x plus g of x. So in other words, we want to figure out what is the resulting equation when we combine these two functions by adding them, right? So we're getting a general equation here that will work for any x, not just a specific x input, okay? So let's do it. Don't overcomplicate. We really are just going to add these two functions. We're going to add f of x's equation to g of x's equation. So h of x is defined as the sum of f of x and g of x. So f of x is x squared minus 3x minus 4. Again, I like to use brackets just to make sure I'm keeping track of, you know, what I'm doing with these two equations. And then we're adding g of x. So we're adding 2x minus 1. And now all that's really left to do is simplify. So I've got x squared minus 3x minus 4, a plus here, so I don't have to worry about any double negatives or anything like that. I'm going to add the 2x. I'm going to add the -1. In other words, I'm going to subtract 1. And now let's just combine like terms to finish simplifying this thing. X squared, no like terms to combine with it. It's just by itself. -3x plus 2x. Well, that's going to leave me with -1x or -x. So I combine those. And then -4 minus 1. Well, that's -5. Combining the constant terms there. And that's really all there is to it. That's h of x. X squared minus x minus 5 is the result of adding those two functions together. Now we want to determine the value of h of 1. Well, we just figured out how to find h of any x, right? These are instructions on how to figure out the value of h at any value of x. So we just got to put in 1 for x, right? Literally what this is asking us to do, h of x is x squared minus x minus 5. So h of 1 is 1 squared minus 1 minus 5. Notice all I did there, put in 1 for x. And so h of 1 is going to be 1 squared is 1 minus 5. Well, 1 minus 1 is 0, minus 5 is -5. And that's h of 1. Found the general equation here, and then used our general equation to figure out what h of 1 would be. Put in 1 for x. And it's asking us here an interesting question. How would the result of f of 1 plus g of 1 compare to our result in b? Well, it should be the same, right? This is just saying figure out what f of 1 is, and then add whatever g of 1 is, right? We figured out in general what happens when you add these two functions, and that should work at every x. So it should be the same. Don't believe me? Well, that's good, right? Don't take my word for it. Let's test it out. Okay? Adding the outputs separately should produce the same result as first adding the equations and then inputting a 1 to get our new output, right? It really is just kind of reversing the order. We could figure out the output of this and the output of this and then add them, Or we could add them and then input our x to get the output of the combined function. So we did that second option here. Let's just, see what would have happened if we had done it the other way. So what is f of 1? Well, f of x is x squared minus 3x minus 4. So f of 1 is 1 squared minus 3 times 1 minus 4. So f of 1 squared is 1, minus 3 minus 4. 1 minus 3 is negative 2. Negative 2 minus 4 is negative 6. So there we go. F of 1 is negative 6. What is g of 1? And then we're going to have to add them. Well, g of x is 2 times x minus 1. So putting in 1 for x, I'm going to have 2 times 1 minus 1. So g of 1 is, 2 times 1 is 2. And 2 minus 1 is 1. So what is h of x? Or rather, sorry, what is h of 1? Well, they've defined h as f of x plus g of x. So h of 1 is just going to be f of 1 plus g of 1. And now we've figured out that f of 1 is negative 6 and g of 1 is positive 1. So h of 1 is just negative 6 plus 1, or, hey, look at this, negative 5. Sure enough, same thing. Okay, so it should be. That makes sense. Alrighty. So these are also peppered throughout the notes. You'll see them as you look through the notes. These are just practice questions from your formative assignments, okay, from your practice questions, and they're put into a place in the notes where it would make sense for you to go get some practice with that concept, okay? This stuff is for when I teach this synchronously, so you can ignore this, but it's still a good idea to do. There's just no Google Meet poll, obviously, but this is a good thing to do with yourself, is to kind of, self-assess. Say, how do I feel about this, right? Go try this practice problem now. Okay, I've copied and pasted it here so you don't have to go get your textbook or whatever. You could try it and just see the answer in real time, right? And see with yourself, how are you feeling, right? If not, great. Maybe go try some more examples. Like this is only 3A, maybe try B, C, D, right? Even if you feel, not 100% with it, you could try a couple more practice ones. But this is a good time to, kind of pause the video if you're following along and maybe go try out some practice with the basic stuff, and then we can come back and continue on to multiplying and dividing functions. All right, so we're on to multiplying and dividing functions now. It's going to be the same thing, folks, the exact same thing as adding and subtracting them. But you guessed it, instead of adding f of x and g of x, for example, we're going to multiply the equations by each other, or the outputs by each other, okay? So the exact same ideas apply as with addition and subtraction, except now we multiply or divide. And again, this can be done graphically or for specific outputs by just doing the operations to the y values, right? If you just care about like f of 2 times g of 2, you can just multiply those two outputs together. But if you want to be more general with it, you can also just multiply the equations together, and that will give you the resulting, combined equation. So a few ways it's represented. Again, folks, these all mean the same thing, just different ways of writing it. There's f of x times g of x, right? There's also just f times g of x, means the same thing. And then even just f of x, g of x, how, we sometimes write 2 times x is just 2x. Same idea there. F of x times g of x. Dividing, we could write it, this is like a little more literal. It's just showing us you really are taking f of x and dividing it by g of x. And this is, again, means the exact same thing. It's just kind of showing that, like, it really is a new function. It's what happens when you take f and divide it by g, right? This is f divided by g of x. So let's try one out here. But again, same principles as adding and subtracting. Now we're just multiplying and dividing. So the functions f of x and g of x are represented by the ordered pairs below. Kind of an interesting way of representing a function, but totally a valid way to represent one. This is actually just showing us, it's not giving us the equation or the graph or anything. It's just listing some pairs for us, some ordered pairs. So we've got x's and y's, right? Inputs and outputs, okay? So f of x, these are four 4 points, 4 ordered pairs that work with the function f of x, right? So f of 1 is 4, f of 2 is 6, f of 3 is 5, g of 6 is 3. We want to use this definition of these functions, or this representation of these functions, to determine the value of, first up, f of 1 times g of 1. We'll take a look. What's f of 1? When x is 1, looks like the value of f is 4, right? The output is 4 when the input is 1. So this is f of 1. F of 1 is just 4. So this is just saying 4 times g of 1. What's g of 1? G of 1 is 5. When x is 1, the value of g is 5. This is g of 1. Right? So this is just 4 times 5, or 20. That's f of 1 times g of 1. All right, f of 3 divided by g of 3. So we got to look for the value of f when x is 3. Let's see. 1, no, 2, no, 3. Aha! When we input 3 into this function, the output is 5. So this is f of 3, right? Means this is literally going to be 5 over, okay, what's g of 3? G of 3 is 2. So it's just going to be 5 over 2. Could leave it like that, right? Could just say 5 over 2. Nothing wrong with that as a fraction. I mean, I would actually recommend just leaving it like that, right? Fractions are good. Fractions are a nice accurate way of representing stuff. If you really wanted to call it 2.5, I suppose you could. But no need really here. 5 over 2. Okay. Part C here. Here's a slightly more complicated one. We're doing g minus f over g of 3. Don't panic. We're just combining multiple operations here. So what this is saying is take the value of g of 3, subtract f of 3, and divide it by g of 3, right? Literally, if we were to expand this out a bit, or maybe not expand isn't the right word, but to show it what it's really saying, right? It's saying g of 3 minus f of 3 over g of 3. G minus f over g of 3 is just saying that. So what's the value of g of 3? Well, we already worked out that that was 2, right? So we've got 2 minus f of 3. Again, we figured out that f of 3 is 5. So 2 minus 5 over g of 3, again, right? Well, g of 3 is 2. So 2 minus 5 divided by 2. Well, 2 minus 5 is negative 3 divided by 2. I mean, again, if you wanted, I guess you could call that negative 1.5, but fractions are our friends, right? Fractions let us represent stuff in a convenient and accurate way. And there we go. We just did all of those. Alrighty. So a similar one here where now we're going to, determine f times g of 1 two different ways. Once by performing the operations on the outputs of the functions individually, and then once by doing the operations with the equations themselves and then inputting our 1 to the result. Okay, so first up, let's do the operations on the outputs. So here's f of x, here's g of x. To do f times g of 1, well, if we're using this method, first we got to figure out what f of 1 is. So f of 1 is going to be, I put in 1 for x, right? So 1 squared minus 3 times 1 minus 4. 1 squared minus 3 times 1 minus 4. That's going to be 1 squared is 1 minus 3 times 1 is 3 minus 4. 1 minus 3 minus 4 is negative 6. Yeah, negative 6. Okay, ooh, I did something bad there. I worked side to side. Don't show your work side to side, especially on the diploma. But I was just trying to save some room. Okay, that's bad of me. Let's do g of 1. G of 1 is 2 times 1 minus 1. So g of 1 is 2 times 1 is 2 minus 1. G of 1 is 1. All right. All right, I had to fix that. That was bothering me that I worked sideways like that. So there we go. A little easier to see now, hopefully. G of 1 is 1. F of 1 is -6, like we worked out. Okay, so to figure out f times g of 1, right, we really can just take, well, f of 1 is -6. G of 1 is 1. So f times g of 1 is just going to be f of 1 times g of 1, right? F of 1 times g of 1. And that's going to equal -6 times +1, which is just going to be, of course, -6. But we would get the same result if we performed the operation on the equations first. Now, again, this is going to seem, especially for something like this, it's going to seem like a lot more work, right? But sometimes, and it is, for some, like if I just want to know f times g of 1, I would do this. I would figure out f of 1, g of 1, and then multiply those outputs together, right? But if we wanted to know a general equation for what the result is of multiplying these two together for any x and not just a specific value of x, then this is the way to go, right? I mean, this wouldn't even do that, okay? But just to show that we still get the same result, we want to do f times g of x. So let's just figure that out. F times g of x is going to equal, again, f of x times g of x. Well, f of x is x squared minus 3x minus 4. And g of x is 2x minus 1. So multiplying them together, right, I really am just going to take those two equations and multiply them together. Okay, now remember, when we're multiplying two polynomials together like this, all of these terms are being multiplied by all of these terms, right? You might have heard FOIL. Again, FOIL is, nothing magic about FOIL. FOIL is a way of keeping track, right? FOIL, we often say when we're multiplying a binomial by a binomial, first, outside, inside, last, right? If you get too hung up on FOIL and treat it like, the magic rule, you'll miss that really all FOIL is doing is making sure that every single one gets multiplied, right? So here we can't rely on FOIL because there's 3 terms and 2 terms here. But if we understand that foiling really just means making sure you multiply all of these terms by all of these terms, then you don't have to change anything about the way you approach this or think about it, right? Again, don't get too hung up on FOIL. That's just a trick you're sometimes taught to make sure you did multiply everything together. It's like a checklist to make sure that all of the terms got multiplied. So all that means is I need to multiply the x squared by the 2x and the minus 1. Then I need to make sure this negative 3x gets multiplied by the 2x and the minus 1. And then the negative 4 gets multiplied by the 2x and the minus 1. So let's go ahead and do that. X squared times 2x, 2 times x times x times x, right? X times x times 2 times x. That's going to be 2x cubed, right? X squared times x is x cubed. And then x squared times negative 1, well, that's negative x squared. And there we go. This term has been multiplied by both of these. Let's move on to this term. Negative 3x has to get multiplied by 2x. That's going to be, well, negative 3 times 2 is negative 6, and then the x times x part can simplify to x squared. And then negative 3x times negative 1, negative times a negative is a positive, so I'm going to have positive 3x. Uh-oh, should have left myself a little more room here. Oh well. Lastly, the negative 4 has to get multiplied by the 2x, so that's negative 8x, going out of the box a bit, and negative 4 times negative 1 is positive 4. Negative times a negative is a positive. All right, so we did it. We multiplied all 3 of these by both of these. Now we just got to simplify a bit here. So there's nothing to combine with the x cubed. However, I've got 2x squared terms here. I've got a negative 1x squared. So a negative 1x squared minus 6x squared leaves me with negative 7x squareds. And then a plus 3x minus an 8x, that's going to give me a minus 5x plus 4. Oh boy, that's not a very good plus. There we go, a little bit better. All right, so that is f times g of x. And now we're going to use that we're going to use that equation to figure out what is f times g of 1, right? Now we know what f times g of any x is going to be. Let's figure out what f times g of 1 is going to be. And just like any function, that just means we're inputting 1 as our x. So 2 times 1 cubed minus 7 times 1 squared minus 5 times 1 plus 4. That's going to equal 2 times 1 cubed is still just going to be 2 because 1 cubed is 1. Same thing here. 1 squared is 1, so minus 7 minus 5 times 1 is 5 plus 4. So f times g, and again, we're expecting this to give us -6 because we already did it, for the outputs individually, right? We should get the same result here. Let's see what happens. So 2 minus 7 is -5, minus 5 is -10, plus 4 is -6. So sure enough, we do get the same result, right? Again, we're really just flipping the order, working out the outputs first and then multiplying them, or multiplying the equations first and then inputting our 1 to get the output of our combined equation. But either way, same result. So another one with graphs here. Again, it's actually really nice when they give us the graphs because the graphs are showing us all these different values of f of x and all these different values of g of x. And then all we have to do is divide them to get h of x, right? So I set up another little table here if we like, right? Again, can you just start taking y values from here and dividing them by y values from here? Yes, but to really just show my work and hopefully make it easier to follow, I just made a little table, right? So I can see, let's just, point out some points here, like when here I've got -5, -5, right? I mean, we could do this at lots of places. -2, -2, right? +2, 2, +5, 5. Could do lots and lots of points there. I just kind of picked a few. Now, if we can find the similar points on g of x, meaning like when x is the same, can we find what g is? For example, when x is 2, right? I think we can, because look, when x is 2, the value of g is 4, right? When x is 5, g is 10. So make it easy on yourself. Don't try to pick, points where you kind of have to estimate. Like I wouldn't try to pick, I don't know. I guess these are all actually not too bad. But try to pick ones where it's easy to read what the x and y coordinates are so that you're not estimating like decimals for no reason, right? Okay, so again, right, when x is -2, g is -4. When x is -5, g is -10. Okay, why am I looking at those points? Again, because all we need to do is take g and divide it by f. So now I know when x is 5, f is 5, g is 10. So h of x is just going to be g, 10, over f, 5, at x being 5, right? So let's just use that to fill out our table of values. So like when x is 5, we said g of x was going to be 10. We said f of x, well, we didn't say it. The graph showed us that f would be 5. So h of x is just g over f, right? It's just 10 over 5, which is 2. So once again, we've got a point, right? On y equals h of x, when x is 5, the value of y will be 2, right? For the graph of h of x. So when x is 5, y is 2. All right. And then we could just continue on this way. You can probably see where this is headed. Look, when x is 2, I've got 4 over 2, right? When x is 2, g is 4, f is 2. So 4 divided by 2, once again, 2. Right? -4 over -2, also going to be 2. So when x is -2, we've got g of x being -4, f of x being -2, but -4 divided by -2 is once again +2, right? Sure enough, even this last one here, when x is -5, the value of g is -10, the value of f is -5, so we're going to do the same thing. When x is -5, g of x is -10, f of x is -5, and -10 divided by -5 would be +2, right? So look at all these points we've got. You can kind of see this is actually just a constant function. This is just going to be h of x equals 2. Looks like no matter where we look, g of x is just twice as big as f of x. So g of x over f of x is always just going to be 2, right? We found that when x was 10, y was 2. When x was -5, y was 2. When x was -10, y was 2 for h of x. Now there's a very important point to think about here. Okay, it's tempting to just go like this. But there's something key here because we are dividing by f. We're going to get into this in a moment here when we start talking about the domain and range of combined functions, but we can get a feeling for it now already with this example. Okay? We are never allowed, remember, we cannot divide by 0. Why? Because that's undefined, right? Why is it undefined? Don't forget what division means, right? Division means splitting it up into that many groups, right? If you're going to share a pizza amongst 5 people, you take the pizza and you divide it into 5 groups. So how do you divide something into 0 groups? How do you take a pizza and divide it into 0 groups? The answer is you can't. That doesn't even make sense, right? If I gave you a pizza and I said, all right, split this one pizza up into 0 groups, you can't do that, right? If you don't split it up, it's just one group, it's one pizza. Okay, so same idea here. You cannot divide by 0. It's undefined. Dividing by 0 just doesn't make sense. And if we look here, there is a place where we would be dividing by 0. Wherever f of x is equal to 0, right? Wherever the y value of f is 0, we would be dividing by 0 for h of x. So this point on our graph, we actually have to leave it out, okay? We have to leave it out. So I'm just going to say when x is 0, when x is 0, g of x is 0. That's not a problem. We can divide 0 by stuff. We can't divide stuff by 0. F of x is 0. That's the problem. Because now we're going to have 0 divided by 0. And that's a problem, right? That gives us an undefined result, right? So we can't include that point on our graph. So how we would represent that, and we'll see this come back a couple times in the course, we would actually just put literally a hole. We call it sometimes a point of discontinuity. We use that terminology more in a later unit, but it applies here as well. And we just represent it like that. See how it looks like there's just a little hole in my graph? Everywhere else, it's fine, right? Everywhere else, I can divide by g, right? Sorry, divide by f. No problems here. I can divide by any number I want, but I cannot divide by 0. That's the one rule when it comes to what you can or can't divide by. You are not allowed to divide by 0 because it just makes no sense, right? It's undefined. Okay, so we would put a little hole there, and we'll circle back to this idea now when we start talking about the domain and the range of these combined functions. So, sorry, I think the video got a little frozen there, but I was just going to say, go ahead and try this one out here now. Okay, use the graphs of f of x and g of x given to determine f times g of -2, right? Look for f of -2, multiply it by g of -2. The graph will let you do that, right? And then try it for f over g of 0. The value of f at 0, the value of g at 0, and divide them. Okay, so take a second to pause and do some practice. And then we'll move on to the domain and range stuff. Alrighty, folks, so let's finish up here by talking about something that has already kind of come up in some of the examples we were looking at, but now we're going to really dive into it here, and that is the domain and the range of the combined functions. Again, combined function, just that's what we've been doing, right? We've been combining multiple functions by maybe adding them or subtracting them or multiplying them or dividing them, okay, doing operations with them. So before we jump into this domain and range stuff that, again, we've kind of seen, probably a good idea to remind ourselves of what the domain and what the range are. What do those terms mean? Okay. Domain tells us what x values we are allowed to put into the function. Okay. Again, remember, like, for example, if I have the graph of y equals x squared, what that's showing me is every point, right? Every point on this graph, the y value is just equal to the x value squared, just using this one as an example, right? So 0, 0 is on the graph because 0 squared is 0. 1, 1 is on the graph because 1 squared is 1. 2, 4 would be on the graph because 2 squared is 4, right? And so that's why, if we think about the domain in terms of what that might look like on a graph, it's the x values that the graph of the function will pass through, right? Because if we can put that x into the function, then it should be an x value that the graph passes through, right? Now, using this example here, y equals x squared, we can see, right? I mean, let's look at it two ways. The equation. Is there any type of x that we're not allowed to put in here, right? Is there any type of number that we can't square? Well, the answer is no, right? We can square any number we want. We can square a negative number, a positive number, a fraction, a decimal, whatever we can think of, we can square it. And the graph backs us up there because look, right? We know the graph of a parabola, it extends, yes, up, well, or downward, upward or downward, but it also extends to the left forever and to the right forever. To the left down to x being negative infinity, and to the right up to x being positive infinity. In other words, our domain is just all real numbers. We can put in any x we want. Now again, this is just for one example. That won't always be the case, but for y equals x squared, we would say our domain, I'll remind you of our set notation and our interval notation. Domain, we would write it as, we open up a curly bracket. That means it's a set. We're about to tell you about a set of numbers, because that's what a domain is. It's a set of, and then the next thing we do is, well, we say what it's a set of. Domain is a set of x values, right? So it's the set of all x's, and then we draw a vertical line. That just means such that. In other words, what we've said so far is I'm about to tell you about a set of numbers. Those numbers represent x values, and then this just means such that, or in other words, the x's that do whatever we say next, right? The x's that fit within whatever we're about to say. Now again, it can be any real number, so we're actually just going to say x could be any. That's the sign element. It means is an element of or is part of. So the set of all x's such that x is part of, and then the r just means real numbers. So what we've just said there is that the domain is all real numbers. It's the set of all x's such that x is any real number. Okay? That, in other words, every number you've ever talked about, right? In your high school math, in university, you'll learn about imaginary numbers, which aren't real, which I know kind of sounds like a joke, but there really are a thing called imaginary numbers. We won't get to those. So that's essentially saying x can be any real number. In interval notation, how we can represent that, we would say from negative infinity up to infinity. Okay, those round brackets mean they're not actually included. That's just because x could never actually be infinity, right? Nothing can ever actually reach infinity or negative infinity. So in interval notation, we just say from the lowest it could ever be to the highest it could ever be. That's the format. Both of these are saying the same thing. This, again, is what we call set notation. This is what we call interval notation. They're both saying the same thing. This says x could be any real number. This says x could be anything from negative infinity up to infinity. In other words, everything, right? There's no number that's not between negative infinity and infinity. Now the range, we've talked about the x's, you probably recall, range tells us what y values can come out of the function. And so again, you can think of the range then as the y values that the graph of the function will pass through. So going back to our example here, and again, this is just for y equals x squared. We'll see lots of different types of functions, but just dipping our feet back into the idea of domain and range here, right? What would be the range of y equals x squared? Well, I want you to think about this two ways, okay? Because again, yes, we could think of it as the y values the graph will pass through, and that's a good way to look at it. But don't lose sight of the fact that what range is really telling us is what y values are possible as outputs. And in this case, it's not actually all y's, all numbers, right? There is a type of y that we will never get with this function. And we can see it on the graph. We can see that y never goes negative, right? We never dip down into the negative y values here. And when we look at the equation, that makes a ton of sense. Because our equation, to find a y, all we're doing is squaring an x, right? And if we square a positive number, that's a positive times itself, so a positive times a positive is positive. If we square a negative number, that's a negative times itself, and a negative times a negative is positive. So there is no way to square a number and get a negative answer, right? So if y is just some number squared, how could y ever be negative? Well, it can't. And when we graph it, that's confirmed, right? The smallest y could ever be is 0. 0 squared would be 0, but then like 0.1 squared would be bigger than 0. Negative 0.1 squared would be greater than 0, right? So this goes down to the point 0, 0, and it never goes lower than that. Its minimum is at 0, 0, okay? Or its minimum is at y equals 0. The vertex is located at 0, 0. So our range here is a little more maybe interesting than our domain because it actually does kind of have something it has to stick to. So in set notation, same thing. We'd open up a curly bracket. We'd say a set of what? A set of y's, okay? The set of all y's such that y must be greater than or equal to 0, right? That's just saying these are the y values that can come out of this function, right? Thinking of it graphically, these are the y values that the graph will go through, right? Sure enough, it never goes below 0, but it does go up forever after that, right? It goes up approaching positive infinity. Now we do still say this. We say the set of all y's such that y is greater than or equal to 0, and then just with a little comma, we clarify that y can be any real number. And if you're thinking, you just said it had to be greater than or equal to 0. I did, right? What this is clarifying is that it can be any real number that's greater than or equal to 0, right? Because, again, it could be y must be greater than or equal to 0, and it must be like an integer. Maybe it could only be 0, 1, 2, 3, 4, right? But we know that's not true. We know that it could be a decimal or a fraction or a rational number, an irrational number. The only really thing that we can't get out is a negative number. So all this is saying is it can be any real number, whether that's a decimal, a fraction, whatever it might be, but it must be greater than or equal to 0, right? So I'll be honest, probably 99% of the time, it's going to be real numbers here, okay? But there could be these restrictions like this. So most of the time, we're going to end our domain or range statements with this. Y will be an element of the real numbers. Pretty rare for these to have restrictions on it must be an integer or a whole number. Now in interval notation, how would we say that? Well, what's the lowest y can be? 0. What's the highest it can be? No maximum, right? It goes up forever. So we say it goes up to approaching infinity, okay? And now key difference here. Y can be 0, right? So to show that in interval notation, we use a square bracket. That's just saying it's allowed to be 0. It can't be lower than 0, but it can get as low as 0. That's what that square bracket says. If I said this instead, that would actually mean that it can't actually be 0. It could be 0.000001, but it couldn't be 0. That's not what we want to say, right? It is okay for it to be 0. We know that if x is 0, y is 0 for this function. And then a round bracket on the infinity because it can't actually be infinity again. Nothing can ever actually reach infinity. Okay, so there's our quick reminder just of what domain and range is, right? Domain, the set of all valid x inputs for a function. Range, the set of all y outputs, okay? And you might be thinking, or, depending on how long it's been for you, well, when would there ever be limits on what we could put into a function, right? Can't we just put whatever numbers we want in? Not always. Not all inputs can always go in. We're not actually always allowed to put whatever x's we want to. And that leads to what we call, unsurprisingly, restrictions on the domain, right? Good name. The domain might be restricted in terms of what x's are actually allowed to go in. Now, two of the most common reasons, I'll be honest, most of the time when we have restrictions on our domain, it's for one of these two reasons in some form or another, okay? The two most common reasons for restrictions on a domain are that you cannot take the square root of a negative number and that you cannot divide by 0, Okay, now we talked about dividing by 0 earlier in this lesson. The square root of a negative number, that one makes sense. Again, the reason that doesn't work, the reason you can't take the square root of a negative, remember, the square root of a number, if I say the square root of, 4, for example, what that's saying, what the square root of 4 is the number that when you multiply it by itself equals 4, right? The square root of any number, even if I just put an x there, the square root of x is the number that if I multiply it by itself will equal x, right? So the reason the square root of 4 is 2 is because 2 times 2, or 2 squared, is 4, right? That's why the square root of 4 is 2. The number that when I multiply by itself equals what we call the radicand, the thing we're taking the root of, okay? So that's the key to understanding why we cannot take the square root of a negative. The number that when I multiply it by itself gives me the radicand. Well, keep in mind, if I multiply a negative by a negative, I get a positive. If I multiply a positive by a positive, I get a positive. So, is it possible to ever multiply something by itself and get a negative answer? No, right? The square root of -1 makes no sense because no number times itself could ever equal -1, right? 1 times 1 is +1. -1 times -1 is also +1. There's no way to multiply a number by itself and get a negative answer. And that's why that's a common form of a common reason we end up with restrictions on our domain is that if we had, just to use this example here that we laid out, if we had the square root of x, that tells us x must be positive. X, the restrictions on our domain here would be that x must be greater than or equal to 0. Because again, x stands in for any number, we often say, but it still can't be a number that would cause us to do something undefined, right? To do something that makes no sense. So we can put in whatever number we want here as long as that number is greater than or equal to 0. Okay? And again, we talked about it earlier. You can't divide by 0 because again, division is about splitting something up into equal groups, right? Dividing a pizza in 2 is taking a pizza and splitting it up into 2 groups. You can't split something into 0 groups, right? Not splitting it at all, that's not splitting it up into 0 groups, it's leaving it in one big group, right? So dividing by 0 literally makes no sense. So these are the two main ways, most common culprits for restrictions on our domain. If we have the square root of stuff, right, that stuff must be greater than or equal to 0. If we have, stuff over other stuff, that other stuff in the denominator cannot equal 0. And when we have x's in a denominator or x's in a root, that's going to give us restrictions on what x is allowed to be. So let's take a look at these then and see if we can work out, would these have any restrictions on their domains? And if so, what are they? First up, f of x. F of x is x squared plus 1, right? So what are we doing with x? We're squaring it, right? Now, are there any rules about numbers we can square? No, right? We can square any number. I could square a negative, I can square a positive, I can square 0. Those are all fine, right? So no restrictions. How would we write that? I mean, we could say the domain is the set of all x's such that x is any real number, right? As long as x is a real number, it's okay. You could also do it in interval notation. X can be anything from -infinity to +infinity. All right, what about j of x though? J of x, we have x plus 2 being divided by x minus 7. Can you see where there are some values of x that might be a problem for us here, right? We're dividing by something that contains an x. That means we got to be careful about what x is, right? Because it is possible to make this denominator 0. It would be 0 if x were 7, right? If x were 7, I'd be dividing by 0. And that is undefined, right? We would have an undefined expression. So, I mean, we can kind of just see, but we could also just write it out, right? We know that x minus 7 cannot equal 0. We're not allowed to divide by 0. Add 7 to both sides to figure out that that means x cannot equal 7, right? I know that one is fairly obvious. X can't be 7, but sometimes they're a little trickier, and this we can just set up an equation to solve for what x cannot be. So what would our domain be? Well, the set of all x's, and there's really only one rule here, the set of all x's such that x does not equal 7. Other than that, it can be any real number. If you wanted to, you could say x is less than 7 or x is greater than 7, but it's a little quicker just to say x does not equal 7. Other than that, it can be any real number. Okay. Interval notation, we could do it. It's a little weird. We would say negative infinity up to 7. Not including 7, so round bracket there. And then we use this U, that means union, just saying I'm stitching together these two intervals, but they're not continuous, so I have to break them up like this. And then not including 7 up to positive infinity. To be honest, set notation's a little bit easier for this one, but that's how you would do it in interval notation. Okay. Lastly, k of x. Aha, do you see a problem we could run into here, right? I see something that could happen. This can't be less than 0, right? We can't have that being less than 0. Otherwise, we're taking the square root of a negative, and as we saw, that just makes no sense, because nothing times itself will ever be negative, okay? So with that in mind, here's how we can set up a little equation, right? We know that 3x minus 6 must be greater than or equal to 0. And now we've just got a little equation to solve here. If I add 6 to both sides, I get 3x. Sorry, I called it an equation. I guess it's an inequality. 3x must be greater than or equal to 6. Now x is being multiplied by 3, so to solve for x, I'll undo that, right? I'll divide by 3. Dividing both sides by 3, I get that x must be greater than or equal to 2, right? So that is the domain. I mean, we can check our work. It makes sense, right? If x is 2, I've got 3 times 2 is 6, minus 6 would be 0. So as long as x is bigger than 2, right, if it were 3, 3 times 3 is 9, 9 minus 6 is positive 3, no problems there. If x were less than 2, what if x were 1? 3 times 1 is 3, 3 minus 6 is negative 3, uh-oh, that gives us the square root of a negative, so it won't work, right? We can kind of tell that, yeah, this makes sense. As long as x is bigger than 2, we won't get a negative here, right? If it's 2, we'll get 0, which is okay. We can take the square root of 0. It's just 0. We can't take the square root of a negative number, though. So our domain would be, in set notation, the set of all x's such that x is greater than or equal to 2. Any real number, right? Any real number that's greater than or equal to 2. In interval notation, well, it can be as low as 2. So it can go as low as 2, square bracket, because it can be 2. It's okay for it to be 2. It just can't be, 1.999. Okay, or lower, and greater than or equal, so it can go all the way up to infinity without ever actually reaching infinity, of course. So there we go. There's our restrictions on the domain. Little reminder just of what domains are and why sometimes they're restricted. Now, let's tie that together with what we talked about today. Again, it's come up throughout the lesson, but now let's really jump into it. Wherever those above functions had restrictions, if we tried to input those restrictions, the result would be an undefined output, right? That's why we have those restrictions. If I tried to put 7 in here, I'd be dividing by 0. That would be undefined. So that's why we have that restriction. If I tried to put 1 in here, I'd be taking the square root of negative 3 like we saw, and the square root of a negative is undefined, right? So that's why those restrictions are there. They would make the function undefined. It breaks the function, so to speak, if we try to put in those values, right? So we just say those are not part of our domain. You can't put them into the function. Now, when we combine functions like we've been doing today, adding, subtracting, multiplying, dividing, okay, all domain restrictions from the original functions still apply to the new combined function, right? Because we're performing those operations on the outputs of the original function, right? Remember, that's what we're doing. We're putting those things into the function and then adding their outputs or subtracting their outputs or multiplying or dividing, right? Which means if either of them is undefined, well, you can't add 1 to something undefined, right? Or divide something undefined by 2. That doesn't make sense. It's still undefined. Okay, so anywhere where either of the original functions were undefined, our combined result is also going to be undefined. Just for a quick example, right? Suppose there's two functions, f of g, and we want to find h of 0, let's say. So f of 0 plus g of 0, right? Well, if f of 0 is 1, g of 0 is undefined, and h of x is just the result of adding f and g of x, right? Well, then h of 0 would be f of 0, so 1, plus g of 0. But maybe g of 0 is undefined. So 1 plus undefined is not 1, right? Undefined does not mean 0. It means it literally is undefined. It is nonsense. It makes no sense, right? Maybe we're dividing by 0. Maybe we're taking the square root of a negative. But it just doesn't work. It doesn't make mathematical sense. So 1 plus undefined also makes no sense, right? So h of 0 would itself be undefined. So you can see here what's going on, right? Is 0 in the domain of f? Yes, it is in the domain of f. It just gives us 1. But it's not in the domain of g. It gives us an undefined result. And since h depends on g, right? H involves the function g. If g is undefined at 0, then there you go. H is also undefined on 0, right? If either of these are undefined, h is undefined there as well, okay? So, putting that idea together, the domain of any combined function, right, any of the operations we've talked about, is the set of all values common to the domain of both of them, right, to both f of x and g of x. Not one or the other, both of them. So they need that, if a value is in the domain of h of x, it needs to be in the domain of both f and g. Both f and g need to be defined for h of x to be defined. So an important note here on division, when we are dividing functions, we're actually going to get an extra domain restriction. You can probably reason why that would be the case, right? Hint, we're dividing. What can we not divide by, right? We also need to consider anything that will make the denominator function 0 because we are dividing by it. So even if that's not a restriction on the original function, we get a new restriction on the combined function purely because of the fact that we're dividing by one of our functions. So just for an example, so you can kind of see what that means, right? F of x equals x squared. No restrictions on x, we can square any number. G of x equals 2x. No restrictions on x there either. We can multiply any number by 2, right? That's legal, okay? Neither of those have any domain restrictions. But if I were to combine them into f divided by g of x, right? If I were to do that, now I've created a restriction for this combined function that neither of them had on their own. Because you can see for f over g of x, if x were 0, I'd be dividing by 0. Right? So even though it's okay for x to be 0 in this function and in this function, it's not okay in the combined function for x to be 0 because then I would be dividing by 0, right? So that has the domain restriction x cannot equal 0, even though neither of the original ones had that restriction, okay? Now for range, I don't entirely agree with this point here. Often we can figure out the range by looking at it and considering what y values could come out of this function, right? Like we were talking about with y equals x squared. Since we're just squaring x, the y outputs could only ever be positive, right? Often we can get there, but in the cases where it's a little more tricky, you can fall back on being able to graph the function. So it says should. I might change that to say can, right? It's not always the best bet to just graph it. Often you can kind of think about what could come out of this function, right? Maybe it can only ever be positive. Maybe it would always be negative. That type of thing, okay? So I'll just change that to a can. But keep in mind, you can graph them, whether on your calculator or on paper, to see what the range actually looks like, to find a maximum value or a minimum value or something like that. So let's see if we can, work through one here and actually find the domain of a combined function, okay? So two functions are defined by f of x equals the square root of 10 minus 2x, and g of x equals the square root of x minus 1. It wants us to first state the domains of f of x and g of x individually, right? So what's the domain of f of x? What's the domain of g of x? So you take a look here, why would we have restrictions on f of x, or rather, what is the domain of this? Well, as long as this is not negative, right, as long as this is not negative, that's okay. If it is negative, that's not okay. That's not part of our domain because, again, the square root of a negative number makes no sense. So let's do f of x. Now, a common student mistake here is to look at this and say, okay, x has to be positive. Be careful, right? X doesn't necessarily have to be positive. 10 minus 2x is what we're taking the square root of, right? This isn't just the square root of x. It's the square root of 10 minus 2x. So our restriction is going to come from the fact that 10 minus 2x, whatever that ends up being, needs to be positive. Only the x's that are going to make that positive are okay and part of our domain. Okay, so I might add 2x to both sides to get 10 must be greater than or equal to 2x. And then you can probably see next step would be x is being multiplied by 2, so let's divide both sides by 2 to get that 5 must be greater than or equal to 2. Oops, no, I divided by 2 already. Sorry, 5 must be greater than or equal to x. Aha! Okay, so another way of saying that, if 5 must be greater than or equal to x, you could also say that as x must be less than or equal to 5, right? If 5 needs to be bigger than x needs to be smaller than 5, okay? So with that in mind, right, notice we didn't end up we found out that x could be negative. In fact, any negative number is safe. Makes sense because we're subtracting this, so if x is negative, we're adding stuff to 10 ultimately. Okay, so our domain would be that x must be less than or equal to 5. So let me just write that. For f of x alone, the domain is all values of x such that x is less than or equal to 5. Other than that, it can be any real number. And then g of x, what's g of x? G of x is the square root of x minus 1. So same idea. X minus 1 must be greater than or equal to 0, and therefore x must be greater than or equal to 1. Right? I mean, we can kind of think about that one, but you can also get there by just algebraically adding 1 to both sides. So x must be greater than or equal to 1. So there's our domain for g of x. The set of all x's such that x is greater than or equal to 1. And as long as that's the case, x can be any real number that's greater than or equal to 1. All right, so we found the domain for f of x individually. We found the domain for g of x individually. Okay, now it wants us to state the domain of h of x, which is just f of x plus g of x. So keep in mind, that means, right, h of x is only defined if f of x is defined and g of x is defined. It's not an or situation, right? It's not okay for one of them to be defined but the other not, because then you have a number plus undefined, which is itself undefined. So we need to figure out what is the overlap, essentially, between these two domains, right? Are there numbers that fit into both of these domains? Because if they do, h of x will be defined for those, right? If not, it won't be defined because one of these won't be, and h of x requires both of them to be defined. So, I mean, you can kind of think about it here, right? X needs to be greater than 1 and also less than 5. We can kind of figure out that x needs to be between 1 and 5, right? If we were to draw this out on a number line, which is kind of a nice way to visualize it sometimes, I find, right? If we did just a quick little number line to think about it, we know that f of x needs to be less than 5. So if this is 5, right, f of x's domain looks like this. Less than or equal to, I should say. Whereas g of x's domain was that x needed to be greater than or equal to 1. Right, g of x's domain looks like this. That's the domain for g of x. So you can kind of see the overlap, right? The overlap is right here. That's what falls into both of their domains. The numbers between 1 and 5, right? That's the domain common to both f of x and g of x. So what's our domain for h of x? The set of all x's such that it's between 1 and 5. So we could say that as 1 must be less than or equal to x, which must be less than or equal to 5. And as long as it's between those two numbers, it can be any real number. So there we go. That's our domain. As long as we're between 1 and 5, g of x will be defined, so will f of x, and therefore h of x, which just depends on both of them, will itself be defined. So really quick before we finish up, let's just take another look at that one we did earlier from the diploma. Because there's actually a question I left out here that was also on the diploma, which asked, could you state the domain of h of x, right? Well, now that we've talked a little bit more, thoroughly about it, I think we could, right? Because again, f's domain was that x must be greater than or equal to -4. We can see that from the graph, right? F is only defined when it's greater than or equal to -4. For g, g was only defined when x was less than or equal to 0, right? Sure enough, when we graphed h of x, look at the domain of our graph. X must be greater than -4, greater than or equal to, I should say, -4, and less than or equal to 0. It's only defined between -4 and 0. That's just the domain that's common to both of these. Greater than or equal to -4, less than or equal to 0. Sure, f is defined when x is greater than 0, but it doesn't matter because g isn't, right? It doesn't matter for h of x if one of these is defined. They both need to be defined. And then on the flip side of that, sure, g is defined when x is less than -4, but f is not, right? So if we wanted to state the domain, it didn't ask, the real diploma question actually did ask us to, but this one in the notes didn't. The domain would be the set of all x's such that -4 is less than or equal to x, which is less than or equal to 0. X is an element of the real numbers. Just the domain that's common to both f and g, because both of those go into figuring out h. All right, so back to the last example here on page 7. Just wanted to go take a look at that diploma one again now that we've talked about the domain stuff. Okay, but if we look at number 2 here, the final example, two functions are defined by f of x equals x plus 7 and g of x equals the square root of x plus 4. Okay, it wants us to state the domain of f times g of x. Well, again, we can kind of just think about this. What is the domain of f of x? What is the domain of g of x? And then what domain is common to both of those, right? F of x equals x plus 7. Well, we can add 7 to any number, right? The domain here is going to be, because I don't have much room, I'm just going to say that. I'm not going to do the full set notation. Apologies, right? Whereas g of x, well, we can't have a negative. So for g of x equals root x plus 4, we can't take the square root of a negative, which means x plus 4 needs to be greater than or equal to 0, which means x needs to be greater than or equal to -4. So in order to, again, use either of these, and this one's not going to give us much in terms of restrictions really, right? It might here, but, well, I guess not here because f's on top. But again, x could just be any real number. This one though, again, if x needs to be greater than or equal to -4 for g of x to be defined, then anything that involves g of x is going to need x being greater than or equal to -4 for it to be defined, okay? So what is the set of numbers that is common to both f and g? Well, again, if we think about what is f times g of x, it's going to be f times g of x is just going to equal x plus 7 times root x plus 4. Guess I didn't need to put that in brackets, oh well. Okay, this has the domain x could be any real number. This has the domain x must be greater than or equal to -4, right? So you can probably see that our restriction on our combined domain here, it's actually just going to be x needs to be greater than or equal to -4, right? We don't get any restrictions from this one. We're not dividing by this one or anything. That would change some stuff. We'll see that when we get to that last example there, okay? But again, even if you just multiplied this all out, you could kind of tell that all we're going to end up with is a square root still with an x plus 4 inside, And therefore, x just needs to be greater than or equal to negative 4, and we won't have a restriction. Or we won't have a problem, I should say. We do have a restriction. So our domain would be, for f times g of x, the set of all x's such that x is greater than or equal to negative 4, right? This domain just needs to include the domain of both of these. This one, no problems. X could be any real number. This one, okay, x needs to be greater than or equal to negative 4, right? So does this satisfy both of these? Yeah, right? This isn't breaking any rules here. It's not breaking any rules here. In fact, that's where it came from. So that's the domain there. Now, what about f over g of x? Let's take a look at that. F over g of x. This might give us a new restriction because we're dividing by one of our functions. So let's just, if we want to look at it to kind of visualize it here, f over g of x is going to be, f is x plus 7, and g is the square root of x plus 4. Now, just like before, we cannot take the square root of a negative. So we're still going to have the fact that, right? I mean, on its own, we would say x must be greater than or equal to negative 4, right? But we also can't have this be 0, right? We also cannot have this equal 0 because then I would be dividing by 0. So that's going to change this a bit. We were saying x must be greater than or equal to negative 4 because it's okay to take the square root of 0. That's just 0. What's not okay is dividing by the square root of 0 because that would be dividing by 0, right? So that's going to limit this domain slightly more. It's not x could be greater than or equal to negative 4. It's actually just x must be greater than negative 4. Not greater than or equal to, just greater than, right? X is, our denominator there cannot be 0. So that's going to change things here. So very similar looking, but slightly different, right? That means our domain is x such that x is greater than negative 4. Strictly greater than, we say, as opposed to greater than or equal to. Okay, and again, that's just because x plus 4 must be greater than or equal to 0, but also the square root of x plus 4 must be not equal to 0, right? That's just combining those two ideas. We need it to be positive because we're taking the square root of it, but we also need it to not equal 0 because we're dividing by it. All right, last one here for lesson 1, the domain of, just flipping these around now, and now we're dividing g by f. So again, just to visualize, g of f of x is going to be, just flipping our numerator and denominator from the last example, root x plus 4 over x plus 7. Okay. Now again, still, we are taking the square root of this stuff, right? So this is going to show us we need x plus 4 to be greater than or equal to 0, and therefore x still needs to be greater than or equal to negative 4, right? Our numerator, that hasn't changed it. We've gotten 0 back, so to speak, compared to this example, because it's okay to have 0 in our numerator. We can divide 0 by stuff. We just can't divide stuff by 0. 0 over stuff is just 0. It's not undefined, it just equals 0. Dividing by 0, that's what's undefined, which leads nicely into this fact. X plus 7, we're dividing by it, so x plus 7 cannot equal 0, and therefore x cannot equal negative 7. Okay, so with that in mind, what's our domain? Now, sometimes this happens. Look, if x needs to be greater than or equal to negative 4, could x ever be negative 7, right? Well, no, because negative 7 is less than negative 4. So not always going to be the case, but in this example, it turned out that like this takes care of this, right? Saying that x needs to be greater than or equal to negative 4 actually takes care of the fact for us that x cannot equal negative 7. So we don't actually need to say both of these, right? If it were true that these were two, things where this could be true without this being true automatically, then you would need to list both. But in this case, if I just say this, x must be greater than or equal to -4, I've actually taken care of both of them, right? No need to specify that x cannot equal -7 because this already tells us that x cannot be -7, right? X has to be greater than or equal to -4. That takes care of this one, right? If I tell you that I am older than 20, I don't need to also tell you that I'm older than 10, right? Automatically, if I'm older than 20, I am older than 10. Kind of the same idea here. If x has to be greater than or equal to -4, we don't have to specify that it also can't equal -7. We already knew that if it had to be greater than or equal to -4. All right, so that wraps up lesson 1. Here is one for you to try that, practices that stuff. And then from there, you can work on your other practice questions. Be sure to reach out, as always, send me an email or book a meeting with me if you want to go over some questions or concepts. I'm always happy to help, but there you go. Lesson 1 done.